Hey everybody, here I have another thing which is very interesting. I tried to lately I heard the news about the Artemis II that they flew around the moon, and I tried to implement a concept, a very shallow concept of how a spaceship can move around an Earth or any sphere. And the thing was that I wanted to do more, but right now here I managed to somehow write a code that shows uh, in a singular in a position you will send your spaceship in a position that in that position with a constant speed it will stay on an orbital on a circular orbit, something like that, if I'm saying correctly. It will stay in that the path, so spaceship won't crash down or won't go outward. So it will stay there and bound to the Earth, Moon, or any sphere that you imagine. And generally, when the crew, the spaceship, is on the autopilot, they have a program, they have a software that control the spaceship. So basically, it's a code like conceptually like this, tied with the physics law to control the spaceship and move it smoothly around the path. And it was pretty fun. And I want to show you my code here, how it works. Um, so yeah, we have some constant here. We have moon, we have the radius of the moon, we have the spaceship mass, we have the altitude. This target altitude is the altitude that, for example, I wanted to be there, the spaceship wanted to be there and stay stable. So I set it here. The max time is the time frame that in the program we define that this time frame is the time frame that we calculate everything. It's our frame by frame. The max time is the time, but we calculate the time on each frame. This dt, the 0 1. Okay, so we are moving instead of 1 second, 1 second. We are moving 0 1 0 1 0 1 like this, and then I set a position of the moon. So my coordinates are like, I had it here. Yeah, are like this. I have a coordinate system. At the center of this coordinate system, 0 0 is a moon, and the spaceship is around this object, the moon. So the first position of it is the position of the moon is 0 on the x and 0 on y. And I use double because of the precision. Here we need precision and the calculation. And also the whole implementation, this implementation is very easy. I mean, it's not very deep and robust. It was with the basic concept of the programming in C. So you can do it too. If you enjoy physics, because this is the majority of this code is about physics. And yeah, you set the position of it, you set the position of moon, you set the position of spaceship, which at the first for example, we are above the moon in one of the axes. The x-axis is the moon radius plus altitude that we want. For example, we put the spaceship over there. This is the job of the shuttle. it was shuttle booster or shuttle, when they shoot the crew or the spaceship into the space, we put the spaceship into that orbit. So for example, we are assuming that we put the spaceship directly in that altitude, the required position. This altitude is the distance from the surface of the moon, but we need also the radius of the moon because of that's the position. And here the center of the moon is 0, so this is the actual position, is this distance plus this distance, this little distance. And yeah, the rest of the thing is that calculating the velocity and both axes. This is the initial velocity that we need. If you start with this velocity, if your spaceship starts with this velocity, it actually stays stable, because we conceptually, this is not actually correct, but this speed is actually a speed that caused by a moon. Okay, the acceleration of the moon over the spaceship at that altitude, at that distance, it causes a speed. So it has an initial speed, and then I declare some prototype here for the function I will using here. We update the position of the spaceship at any time, because velocity change at any time, so we multiply it by the frame of the time, so we get the new position, easy peasy. We calculate the altitude, it's easy. We subtract the moon position from the spaceship position, so we get the dx, the altitude over x and over y, and we get the direct distance using the Euclidean formula. And we then subtract the distance, because it comes from the center. No? The moon position was 0, 0, so when we calculate the Euclidean distance, it will be the distance from the center of the moon to the position of the spaceship. So we subtract the distance from moon radius, so we get the altitude, which is the altitude of the surface of the moon to the spaceship. And we update the velocity. Then we need to update the velocity at each time frame we're moving forward. And generally velocity stays same, stays still, doesn't change, because you need to stay in that velocity at that altitude. If you keep your velocity, you will be stable and you will not crash. So you simply calculate the r, the acceleration, and you make them to be in the unit because of the distance. You calculate the unit vector, and you use that unit vector dt time frame and acceleration to calculate the new. You actually add it to the previous velocity to calculate the new velocity over x and over y. Because when I'm saying velocity, I mean vector. The magnitude of velocity vector is the speed, which is another thing which we need it here to check the stability. We need at any time, we need to see we have the required speed to stay in that orbit or not. If our speed is low, we will crash down. If our speed is too high, we'll go outward and we lose the orbit. We will be lost in space. So the record speed has to be specifically in a good area of the good interval, so we won't crash down to the moon, and we will not go we will not go outward. And we update the velocity vector here. We also have a check stability function, which again calculate the speed, record speed. So you have a record speed, which is this, which depends on the g, which is the gravitational constant, moon mass, and your distance from the center of the moon, which is altitude plus moon radius. Simply, if you know your distance from the center of the moon, you know the moon mass, and you know the gravitational constant, you can calculate the record speed to stay in that orbit in that distance. So this tolerance is because I used to think that these things has to be really precise, but generally you can have some tolerance. So your speed hasn't be it must not be exactly, for example, 24. It can be 24, it can be 25, it can be 23, but you are still in that same orbit. You will stay there. So we add a tolerance here, and we said that if these fabs will calculate the absolute value. If the difference of the speed that we have it right now from the required speed to stay stable in that orbit is more than tolerance, we are not stable. If it's less than tolerance or equal to tolerance, we are stable. And give me a second, I have to answer a call. How can I stop this? Hey, I'm back. Sorry for the time and the pause, but time passed. We were at where check stability. So here I told you that we actually check the speed, the recorded speed for staying in that orbit. But in the reality, we are not just using the speed; we are also using the angular speed, and also position, and the condition of staying stable is much more robust and much more strict. There's more condition to make sure that spaceship stays in the orbit. Once again, I'm saying that I'm not a physics student. I was just interested in this mechanic and how these things actually working. So I try to implement this. This is a very shallow and naive implementation of such things, but it has a conceptualized structure of a code that can and should handle the autopilot of a space. And of course, in reality, the code is much more complex. And then in the previous video, I was saying that there was a confusion here. The DT is the frame, each frame of a time unit. Our time unit in the program is passing away, is measured by DT, and max time is the whole time that our program will be running. So 15 unit of time is the whole program time, and dt is 0.1 unit of time. So dt is in time frame, each frame, and max time is the whole time that the program will get run, because we will use it in the loop of the program. Then after the check stability, because getting the position, update the velocity, and all of this stuff, we need to check the stability at this new position. If we are stable, everything's fine. If spaceship is not stable, so we're gonna crash into the Earth, Moon, or we're going to fly into the space and get lost. This normalizer was actually for the next step of this program. I wanted to draw the this schematic, all the dot spaceship and the moon on the terminal, so you can see that we have a spaceship which is going around, flying around the moon, and all of this stuff. But for now, I didn't implement anything. But the function is here. It is normalizer. It has a scalar because we need to normalize, because these, for example, these numbers are very big. So for the position, altitude, and all of this stuff. So we need to normalize them to be able to show them in the terminal. And the actual main function, we have a for loop. We use the max time, we use the dt. Time will move forward by dt. We calculate the altitude, we update the velocity, then we get the magnitude of the velocity vector, which is the speed, and then we check the stability with altitude and the speed. If it's stable, everything's fine. If it's not, we're gonna crash, or anything else happens, something bad will happen. And then after check stability, everything's fine. Then we update the space position, and then again we do all of this calculation. Here I print all of it: time, altitude, speed, and stability. It will be 0 and 1. You see, we don't have the true false like a boolean stuff. And the US slip for pausing a little bit the loop, so we can see the change of the values. And here, after a time of 5, I add some noise into the position. But again, this is not really correct to make the spaceship unstable. Yes, to make the spaceship unstable, we have to add the noise into the speed. So in an orbit, if you change the speed, you make it unstable, for example. But changing the position too can make it unstable as well. So I will run the program. I think I already compile it, but let's do it again. Compile it, and space. You can see it on, and finish. Here stability is 0. The spaceship is not stable anymore, but here it's stable at this time, at this altitude, speed. Here it's not stable, and then it's stable again. Here is stable, not stable, stable. It's just and a little bit here. This fluctuation is not actually true, because some fluctuation, like in our implementation is not very robust. So this fluctuation can affect the stability checking. So stability will be 0, but our spaceship is still stable. And 1 1 1 1 1. Actually, after the 5, right? 5 is here. So see, position is changing, speed is still changing, position is changing, speed is still, and then at some point speed also changing. The changing in the speed will lead us to changing our stability, and that's it. it's very, very, very cool. Do it yourself if you love physics and you enjoy it. Thank you so much.